Welcome, class. I wanted to discuss some ideas that are going to uh, affect us in this class, and that is mathematical proof. So we're going to kind of walk through, and I have an example one that you probably already know, but we'll kind of walk through the process when we talk about a mathematical proof. So first, a mathematical proof is an argument. It is there we go. Okay. An argument that shows a logic flow between the assumptions and the conclusion. Now, it's not just straight from assumption to conclusion. There's a flow. So usually there's more than one thing. And the statement you're trying to prove is the conclusion. What you start with is your assumption. So the statement you're trying to prove, conclusion. You can use axioms, definitions, postulates, theorems, and previously proven statements as assumptions. So you're taking your beginning statement and you're moving it through these assumptions to get to your conclusion. So you start with the assumptions as you work, and they're often just some idea, whatever, and you work towards the conclusion. So this could be the idea of proving that what's the more common one that most of you know is the a squared plus b squared is equal to c squared. That's Pythagorean theorem. And that's a conception. And there's more than one, this beginning statement. And then there's more than one way to prove it using different assumptions. And you work towards the conclusion that that's true. I will say that a proof is not a picture or an example. If you've used regular numbers in there to prove something by giving an example, that's not a proof. If you draw a picture, that is not a proof. That being said, a picture can absolutely complement a proof, but it cannot be the entire proof. And in classes like higher geometry, that you can assume that there will probably need to be a picture. Not always, but usually, but it cannot be the entire proof. Also, an example, you throwing numbers out there to prove a midpoint or whatever, is not a proof. That is just you doing some computation to show that it works in that particular case. But since there's an infinite number, an infinite amount of numbers, that isn't a justified proof. So let's look at an example. So the example is a famous proof example. You've probably heard of it. If A and B are lengths of the legs of a right triangle and C is the length of the hypotenuse of the right triangle, then A squared plus B squared equals C squared. This is Pythagorean theorem, and we're going to prove it. There are, if you've taken like a math history class, you know there's hundreds and hundreds of these, and we're going to work through them. One of them. We're not doing all of them, of course. Consider the dissection given below of a square with side lengths a plus b into 4 right triangles with side lengths a and b, along with a quadrilateral in the center, like this. So we have side lengths a plus b in our square, and there's our right triangle in each corner. That is the definition of a square. They have this 4 right angles, and side lengths. The side lengths are the same, a plus b. So that's the definition of a square. So we have this square, and now we're going to use it. And so first, we consider that dissection, and then we have 4 triangles are all congruent to the original right triangle, since they are all right triangles with leg lengths a plus b, so each of them have a plus b, and all of them have the same hypotenuse of c. Then, and this is how we go about proving this. We take what we had, So we were given the original statement, and we're going to start with this dissection, this cutout of how we're putting it together. That is our a plus b square, right? Our squared piece with side lengths a plus b. And from that, we start with, okay, so these triangles are all the same. So we have 4 of them. And also each angle, each of the angles of the interior quadrilateral, this quadrilateral, have right angle, because this angle and this angle, so these 2 angles must equal 90. The 2 non-right angles in the triangles sum to 90, since in Euclidean space, the angles of all triangles sum to 180 degrees. So this whole triangle, every one of these angles must add up to 180. We're in Euclidean space. And since this one right here in the corner is 90, these 2 together must equal 90. But this angle here and this angle here are the same. So this plus this must equal 90. The full segment, a line, is 180. So since this is 180, and this plus this is 90, this must also be 90. Now we have that the interior quadrilateral angles are all 90. And since using the definition of a quadrilateral of a square, we have that the interior angles of this inside quadrilateral, interior quadrilateral, all have angles measuring 90, and the sides are all C, so they're all the same side. It is a square. Now, why do we have to prove this? Well, we kind of needed to prove this because we're going to use the area of this big one, which we do know is a square, and the area of these 4 triangles and the area of this. So we need to know that it's a square. We can observe that the area of the large square is the sum of the area of the 4 triangles and the smaller square, right? So that big one must equal all 4 plus the smaller. Thus, the area of the larger square is a plus b squared, one side times the other side. The area of each triangle is 1/2 of a times b, right? So 1/2 a times b. And the area of the interior square is just c squared, c squared. So length and width, however you want to think of it. So with that, we have the quantity of a plus b squared is equal to 4. There's 4 triangles, so 4 times 1/2 of AB, a times b, plus c squared. And then we expand that out, and we get that we have a squared plus 2ab plus b squared is equal to 2ab plus c squared. Now, subtracting the 2ab from both sides, we have a squared plus b squared equals c squared, as we claimed, or as was claimed in the theorem. Therefore, if a and b are lengths of the legs of the right triangle, and c is the length of the hypotenuse of the right triangle, then a squared plus b squared equals c squared. Now, some people, some mathematicians do not, once they get to the second to last line, so the line, this line, as claimed, they like to just consider it done. I find that students don't always know that. So I always add a statement basically connecting what we were supposed to be proving with what we just found. And that's my usually therefore, but not always. And even more so than that, I always end with a either QED or I've seen just a box. Sometimes there's a shaded box like that one right there that I just put up. Just something to actually verify that this is the end of this proof. Now, I want to say that in this proof of the Pythagorean theorem, we started with assumptions, and that was that A and B were lengths of the legs, and C was the length of the hypotenuse of the right triangle. We then gave deductive argument, whose conclusion was the desired outcome, A squared plus B squared equals C squared. Each step in the argument was justified logically from results either previously established to be true, either earlier in the argument or from somewhere else. But I want to notice that we invoked facts from geometry and algebra in the course of our proof. For example, we accepted as true all of the following statements. The sum of two non-right angles in a triangle is 90 degrees. Well, I did state that this comes from Euclidean space, but I didn't say by the definition of a triangle in Euclidean space, the angles all sum to, which would have been clearer. I probably could have said that. And there's probably enough room here, but space was getting tight. The area of a square is the square of the lengths of its side. This idea of A plus B squared, length times width, we didn't actually, we're taking that for granted because I didn't prove that that's the area of a square. There is a proof saying that that's the area of a square, but I didn't show it here. That we can subtract equal quantities from both sides. This idea here, right here, this point here, where so this idea here of 2AB, wait, can I do this? Let me do this. So this piece where I said, well, we have this, and we have this. So we can subtract 2AB. Well, I didn't prove that we can subtract equal quantities from both sides of an equality to obtain a new equality. At no point did I prove that. That's an algebraic identity. That's an algebraic property, but I didn't do that. Also, this right here, that this piece here is equal to all of this, right? I didn't prove that. We took that for granted. Or I took that as accepted. So in order for the proof to be completely valid, I would need to justify all of these additional facts that we've invoked throughout this. Of course, to justify each of those facts, I would probably need to invoke further others and then prove those and justify those. It's not hard to see that this demand for justification would never end unless at some point we simply declare some fundamental assumptions, and then just everything in terms of those assumptions. Normally, those fundamental assumptions are called axioms, and I could invoke them all the way down to axioms for this algebra here. That's not really too bad. I could invoke postulates, which would give me the triangles in Euclidean space. So this piece of line, I could invoke some postulates that would prove this statement. And then I could go through the idea of the area of a square, right? The area of a square being this, that would be another postulate. So I could actually go all the way down to the axioms or the postulates. When you're writing proofs, you need to find out where you need to go, how far. If you're writing a proof for geometry, you will probably not need to prove the algebra behind it, unless that algebra is essential to proving the piece you're talking about. If you are proving something in algebra that you can use geometry to explain, you may have to prove some ideas to justify it. When we put little proofs inside, we call them lemmas. But this is the beginning. So this is the setup. My hope is you guys have already seen these ideas. None of this should sound new to you guys. But if it is new, we will explore it a little bit. This class, we don't go into too much detail. I assume you know how to do some of these, and we're going to do some proofs. Not deep ones by any means, and I'm not a real hard grader that way, but I do expect it to look like a proof. I expect it to start with proof, and then you tell me what you're doing and justifying each step. If I don't see justification of your steps, we're going to have a problem. Okay. So please be aware that this is a class where you will need to write proofs, and you are expected to know how to do that. All right. I hope that helps. Hope this is a beginning step to help you guys. All right, you guys, have a wonderful day.